A phone battery can look healthy indoors, then plunge towards zero after a few minutes in freezing air. The strange part is that the energy has not always vanished. Cold changes how a lithium-ion battery moves charge inside itself, and that can make a partly full battery behave like one that cannot keep up. So, before we treat the battery percentage like a tiny fuel gauge, we need to slow down and look at what the phone is actually measuring. A lithium-ion battery is not just storing energy, it is delivering that energy through moving ions, flowing electrons, and a voltage that changes under load. Cold interferes with that delivery system first. A phone that showed a comfortable charge outdoors can suddenly report low battery, or even shut down when the air is very cold. That is the observation we are starting with, not the explanation yet. Imagine leaving a warm apartment on a winter morning with your phone at 40%, then checking a map at a bus stop and watching the number fall much faster than it did indoors. In some cases, the screen may warn you about low power after only a few minutes, even though the phone seemed usable moments before. The central question is whether the battery has truly lost all that stored energy, or whether the cold has changed how easily the phone can get that energy out. A phone battery is not a tiny fuel tank with a simple gauge floating inside it. It is a chemical system that has to move charged particles through materials, while the phone asks for steady electrical power. The battery percentage is the phone's best estimate of usable charge under the conditions it can measure. Cold weather can make that estimate look strange because usable power and stored energy are related, but they are not exactly the same thing. A useful comparison is a thick drink through a straw. The drink may still be in the cup, but if it becomes harder to pull through the straw, less reaches you when you ask for it quickly. That comparison is only an analogy, because a battery is governed by electrochemistry, not liquid flow. Still, it points toward the same practical idea. Energy can be present while delivery becomes harder. In the cold, the phone may see voltage drop under load and interpret that as a low battery condition, especially when the battery is already partly drained or the phone is doing something demanding. There is some uncertainty in the exact percentage you see, because it depends on battery age, phone design, temperature, and recent use. So the mystery is not simply that cold air deletes charge. The more precise question is how cold changes the battery's ability to provide usable electrical power right when the phone needs it. To answer that, we need to look inside a lithium-ion battery and see what it is trying to do. A phone battery is not a tiny fuel tank that simply pours out charge until it is empty. It is an energy delivery system, and it works by keeping two different materials ready to trade charged particles in a controlled way. In a lithium-ion battery, those two materials are called electrodes. One electrode is the anode, and the other is the cathode. During normal use, lithium ions move inside the battery from one electrode toward the other. A lithium ion is a lithium atom that carries a positive electric charge because it has lost an electron. The ions do not move through the phone's wires. They move through the electrolyte, which is the material inside the cell that lets ions travel between the electrodes. At the same time, electrons take a different route. Electrons cannot freely cross the electrolyte in the same way, so they flow through the phone's external circuit instead. That electron flow is the useful part for the phone. It powers the screen, the processor, the radio, the speaker, and all the small circuits that make the device feel alive. Think of the simplified diagram as a map, not a photograph of the real chemistry. Inside the cell, the labels show the anode, cathode, electrolyte, and lithium ions moving through that internal path. Outside the cell, another label shows electrons moving through the phone's circuit before returning to the battery. The key point is that the battery needs both motions to cooperate: ions moving inside, electrons moving outside. The exact materials vary by battery design, but this basic division of labor is central to how phone batteries deliver energy. Now we can ask what cold weather changes in that carefully coordinated movement. Lower temperature slows many chemical and physical transport processes, and a phone battery depends on those processes every time it delivers power. Inside a lithium-ion battery, lithium ions still move through the electrolyte and into or out of the electrode materials, but cold conditions make that movement less easy. One reason is that the electrolyte becomes less helpful as a pathway for ion motion. The ions have less thermal energy, so their random motion is slower, and they bump through the liquid or gel-like material with more difficulty. At the same time, moving into the tiny spaces inside the electrodes also becomes slower, because those insertion and removal steps depend on atomic scale motion. So the battery is not empty just because it is cold. It may still contain plenty of stored chemical energy, but that energy is harder to access quickly. A useful comparison is a hallway at room temperature versus the same hallway after the floor becomes sticky. People can still walk through it, but the flow slows down, and a crowd cannot move as easily when everyone tries to pass at once. In the battery, the crowd is lithium ions, and the sudden demand might come from opening the camera, loading a map, or turning up screen brightness. At room temperature, ions can move smoothly enough to keep up with that demand. In the cold, they move more slowly through the electrolyte and electrode materials, so the battery has a harder time supplying current on demand. The next thing this slowed ion traffic changes is the battery's electrical behavior, because the resistance inside the battery rises. Internal resistance is the opposition inside the battery that causes some voltage to be lost while the battery is delivering current to your phone. A lithium-ion battery does not send energy out as if it were an ideal frictionless source. Inside it, lithium ions have to move through the electrolyte, enter and leave electrode materials, and keep up with the electrons flowing through the phone circuits. At room temperature, those steps are easier, so the battery can deliver current while losing only a modest amount of voltage inside itself. In the cold, the same ion movement becomes slower and harder, so the battery's internal resistance rises. That higher resistance means more of the battery's voltage is effectively spent inside the battery before the phone can use it. The effect becomes most obvious when the phone asks for a lot of current. Opening the camera, recording video, using GPS, or loading a demanding game all make the battery work harder than simply showing a static screen. Under that heavier load, the voltage drops more sharply, even if the battery still contains stored chemical energy. As an analogy, picture the battery as a water pipe labeled analogy. At room temperature, the pipe is wide, so water flows through with a smaller pressure loss. In the cold, the pipe is narrower, so the same requested flow causes a larger pressure drop before the water reaches the other side. The battery is not literally a pipe, but the comparison captures the important point. Harder internal flow produces a bigger drop under demand. On a voltage graph, this appears as a deeper sag when the phone draws power, with the cold battery dipping lower than the warm one for the same task. There is some uncertainty in the exact size of the drop, because it depends on battery age, chemistry, charge level, and how cold the phone is. But the mechanism is the same. Cold slows ion transport, resistance rises, and the usable voltage falls faster during load. That voltage sag sets up the next puzzle: why the battery percentage can seem to fall so abruptly. Battery percentage is not a direct fuel tank measurement of how much chemical energy is left inside the phone. It is an estimate, built from signals such as battery voltage, recent power use, temperature, and learned behavior from previous charge cycles. That distinction matters in the cold because the phone cares not only about stored energy, but about whether the battery can deliver enough voltage right now. A lithium-ion battery may still contain chemical energy, but cold temperatures flow ion movement and raise internal resistance. When the processor, screen, camera, or radio asks for power, that higher internal resistance makes more voltage drop inside the battery itself. The voltage available to the phone's circuits can sag quickly, even though the deeper store of chemical energy is falling much more slowly. Imagine two gauges side by side. The first gauge, labeled stored chemical energy, creeps downward in a steady way. The second gauge, labeled available voltage under cold load, suddenly dips when the phone has to work hard in freezing air. Your battery percentage is closer to an informed estimate from that second behavior than to a tiny sensor counting every bit of energy like drops in a tank. So a phone at 30% may appear to fall to 10% unusually fast, or it may shut down before the chemical energy is truly exhausted. That shutdown is usually a protection decision, because electronics need a minimum stable voltage to operate reliably without crashes, corrupted work, or unsafe battery stress. There is uncertainty in the exact threshold because battery age, phone model, temperature, and workload all change how large the voltage sag becomes. The key point is that the cold can hide usable energy by making it temporarily hard to deliver, and that leads directly to what happens when the battery warms again. Some of the apparent lost charge can return after your phone warms back up. That sounds strange, because the battery percentage can look like a simple fuel gauge, but a lithium-ion battery is not a tank with a window on the side. Inside the battery, lithium ions have to move through materials and across boundaries, while electrons move through the phone circuit. Cold temperatures slow those internal processes down. The ions move less easily, the chemical reactions respond more sluggishly, and the battery develops higher internal resistance. Internal resistance is the opposition inside the battery itself that makes it harder to deliver current when the phone asks for power. When resistance rises, the battery voltage can dip under load, even though useful chemical energy is still stored in the cell. This dip is called voltage sag. To the phone, a sagging voltage can look like a battery that is nearly empty, so the software may show a sudden drop, throttle performance, or shut the phone down to protect the system. When you bring the phone indoors, the battery gradually warms. Ion movement improves, internal resistance falls, and the voltage can recover closer to what the stored energy can actually support. That is why a phone that showed 12% outside might show 18 or 20% after sitting in a warm room for a while. The energy was not magically created during warming. More of the stored energy became usable again because the battery could deliver power with less voltage sag. The amount of recovery is not guaranteed. It varies with battery age, how cold the phone became, how long it stayed cold, and how the device estimates and protects its battery. Cold can still stress batteries, especially at extremes, but the immediate winter drop is often a temporary delivery problem, more than instant loss of all stored charge. Next, we can see why that same cold day is much harder on an older battery than on a new one. Battery aging changes the starting condition of the battery before cold weather even enters the picture. A new phone battery can usually store more charge and deliver current with less internal opposition. An older battery has typically lost some capacity, which means it holds less usable energy after a full charge than it did when it was new. It also often has higher internal resistance, which means the battery itself pushes back more strongly against the flow of current. Internal resistance is not a separate part you can point to like a wire or a chip. It is the combined effect of chemical changes inside the cell, including slower reactions, altered electrode surfaces, and wear in the pathways that lithium ions use. When your phone asks for power, the battery voltage drops a little under load. That drop is called voltage sag. In a healthy new battery, the sag may stay small enough that the phone keeps running normally. In an aged battery, the same request can cause a larger sag, even if the battery indicator still shows charge remaining. Cold weather adds another layer to the same problem. Lower temperature slows ion movement and raises resistance, so the battery has a harder time delivering current quickly. Now combine those effects. An older battery begins with higher resistance, and the cold raises effective resistance further. Under the same cold load, a new battery might dip but remain above the phone's cutoff point, while an aged battery might dip below that cutoff and shut the phone down suddenly. The stored energy has not necessarily vanished in that instant. The phone has stopped because the battery could not hold its voltage high enough while supplying power. This is why an older phone can feel especially unreliable on a freezing morning, even when a newer phone beside it still works. There is variation between battery designs, usage histories, and software settings, so age is not the only factor. But the mechanism is clear. Less capacity leaves a smaller reserve, and higher resistance makes cold-related voltage sag more severe. Next, we can separate what cold does temporarily from what it does, and does not mean for long-term battery health. Cold does not usually mean your phone battery has suddenly lost all of its stored energy forever. In the short term, cold mainly changes how easily the battery can deliver that energy. Inside a lithium-ion battery, lithium ions have to move through materials and an electrolyte, which is the liquid or gel-like medium that helps charged particles travel between the battery's electrodes. When the temperature drops, that movement becomes slower. The chemical reactions at the electrodes also proceed less easily. That combination raises internal resistance, meaning the battery wastes more of its effort pushing current through itself before the phone can use it. As internal resistance rises, the voltage available to the phone can fall, especially when the phone asks for a burst of power. A simple example is opening the camera on a freezing day. The battery may still show 30%, but the camera, screen, and processor ask for enough current that the voltage briefly drops below the phone's operating limit. The phone may dim the screen, slow performance, disable some functions, or shut down to protect stable operation. That is different from long-term battery damage. Once the phone warms back up, some of the missing performance often returns because ion movement becomes easier again. An older battery has less capacity and higher internal resistance, even at room temperature. So cold can push it past the shutdown threshold sooner than a newer battery. Charging is the separate caution. Charging lithium-ion batteries in very cold conditions can be more concerning for battery health, because lithium may not insert into the battery materials in the usual way under some conditions. Modern phones often include safeguards that slow, pause, or block charging when temperatures are outside the intended range. But the exact behavior depends on the device design. So the practical distinction is this. Cold use can make battery performance unreliable for a while cold charging can carry a greater risk of lasting battery wear if safeguards do not prevent it. Next, we bring this back to the number on the screen, because battery percentage is not just stored energy, it is available performance under the conditions your phone is facing. Cold does not simply erase a phone battery's stored energy. It slows lithium-ion movement, raises internal resistance, and makes the battery's voltage sag when the phone asks for power. Because the phone estimates charge from voltage and battery behavior, that sag can look like a sudden drop or trigger shutdown. When the phone warms, some apparent lost charge may return, though recovery depends on temperature, battery age, and device design.